Swayam Prabha. Digital India. Educated India.
Right, in this particular lecture, we are going to discuss the formulation of the linear programming problems. In our previous class, we have already seen what is linear programming. Further, in this particular thing, we'll take up some problems and try formulating those linear programming problems. You see, particularly in the real world, formulation is one of the very big challenge, because most of the time, it is the formulation of the problem that is going to be very important. The solution can also be done by computer. While solving, obviously, we must also know the concepts and theories that are taught in this particular class, so that you know to interpret the results and which method should be employed and when, right? So those kind of knowledges are also very important. But apart from that, formulating a problem in itself is also a very big challenge. So we begin with a very simple linear programming problem on, you can call it's a product mix problem. So what is this product mix problem that we are having here? A company produces two products, A and B, and there are three resources that are required to produce the products: forming, welding, and painting. The company works for 8 hours a day. If only A would have been produced, number produced would have been 90, 80, or 150 respectively from the three resources. If only B would have been produced, number produced would have been 120, 160 and 100 respectively from the three resources. So if profit per unit for A and B are rupees 600 and rupees 400 respectively, find the optimal production per day for the two products so as to maximize profit. So in this particular problem, the first thing to really look for what is the objective function. So as you can understand, the objective function can be thought of from this particular consideration. What are they? First of all, the profit per unit of A is 600, profit per B is 400. So that would give our, the maximizing function. So obviously, the objective function is one of maximization, and the two decision variables. What are the two decision variables? Number of product A to be produced and number of product B to be produced. So if we let us say product A to be produced is x1 and product B to be produced is x2. So what should be our objective function? Maximize z equal to 600 x1 plus 400 x2. So that is the objective function. What would be our non-negativity constraints? Obviously, x1 and x2 both should be greater than equal to 0. The next very important question that comes to our mind, that if only A would have been produced, number produced would have been 90, 80 or 150 respectively. So supposing the full capacity is to be used in producing A only, so with the forming resource we can make how many products? 90 products. With welding, 80 products. Painting, 150 products. So it's not that all of them will be produced, because you see, to make 1 unit of product A, we need all the three resources, that is forming, welding and painting. So in a sense, we can make only 80 perhaps, because that is going to be our bottleneck resource. But forgetting the bottleneck resource at this point of time, the essential idea is that all the three resources are required, and as far as forming capacity is to be expressed in terms of product A, then it is 90. Similarly, if only B would have been produced, the forming capacity is in terms of product B is 120, in terms of welding is 160, and in terms of painting is 100. So see, if we are producing x1 units of A and x2 units of B, how much of the forming resource are you utilizing by producing product A. Think over. This will be x1 by 90. Why x1 by 90? 90 is the total resource. X1 you are using for the forming, for producing product A. Similarly, x1 by 120 is the resource that you are going to be using, for your other kind of thing. That means uh, for total forming resource that you are going to be using is x1 by 90 plus x2 by 120. Is it not? So x1 by 90 plus x2 by 120 is the total forming resource that you are going to use. So these entire thing, that is x1 by 90 plus x2 by 120, must be less than equal to 1, because total forming resource is limited. Is it not? So that gives us the constraint as far as the forming is concerned. So as far as welding is concerned, what should be that particular resource? It should be x1 by 80 plus x2 by 160, should be less than equal to 1. And as far as painting is concerned, it should be x1 by 150 plus x2 by 100, should be less than equal to 1. So all that thing is mentioned here, that is x1 and x2, they are the number produced for A and B respectively. From the three resources we have, x1 by 90 plus x2 by 120 is less than equal to 1, x1 by 80 plus x2 by 160 less than equal to 1, it is the second resource, and x1 by 150 plus x2 by 100 is less than equal to 1, that is the third resource. So these are the three constraints, and the objective function we have already discussed, that is maximize z equal to 600 x1 plus 400 x2, and finally the non-negativity constraint x1 greater than equal to 0 and x2 greater than equal to 0. Let's go back once again. You see, these are the profit per unit 600 and 400, and those are the different constraints for forming, welding and painting. So utilizing all of them, we have got the objective function, the non-negativity constraints, and the three different constraints. This form of keeping constraints would be not very looking good to us. So we can simply multiply by a common factor, that is 360. Here the common factor, that is 160, and the common factor, that is 300, and translate them, that is 4x1 plus 3x2 less than equal to 360, 2x1 plus x2 less than equal to 160, and 2x1 plus 3x2 less than equal to 300. So that would actually complete our formulation. So look here, this is the LP problem formulated finally. Maximize z equal to 600 x1 plus 400 x2 subject to constraints, 4x1 plus 3x2 less than equal to 360, 2x1 plus x2 less than equal to 160, 2x1 plus 3x2 less than equal to 300, and the non-negativity constraints x1 and x2 both greater than equal to 0. Before we move over, let us also see how the graphical solution of this particular problem look like. So here is a graphical solution for this particular problem. See what we have done. There are lots of information here. First of all, this is the dimension, that is the x1 axis, which is really x2 equal to 0. So this is the dimension which is x2 axis, which means x1 equal to 0. Then these three lines, you see, if you look once again, we do not have equality constraints, we have less than equal to constraints. But the equal to constraint part would be those straight lines. So this is the 4x1 plus 3x2 equal to 360. Why this is the line? Because if you put x1 equal to 0, then x2 should be 120. So 0, 120 is a point. And if you put x1 equal to x2 equal to 0, then x1 should be equal to 90. So that would give this line as one of the constant lines, and If you put 0, 0, then it is satisfied. That means 4x1 plus 3x2 less than equal to 360 would be this side. Why it is satisfied? Because 4x1 plus 3x2 less than equal to 360, putting x1 equal to 0 and x2 equal to 0, that is the origin, is satisfied. So the inequality would be this side. Similarly, same thing about all the three constant lines. 2x1 plus x2 would join 0, 160 and 80, 0. So that is the line. And 2x1 plus 3x2 would join 0, 100 and 150, 0. So adding all of them, the common solution space is OA, B, C, D. That is our common solution space. And it's a feasible solution space. First of all, this is feasible and it is also bounded. It is not unbounded. Because you see, this is a closed area, O, A, B, C, D. Now, this solution space is also a convex solution space, as we have discussed earlier, because if you take any 2 points within this solution space and you join a straight line, you would find that straight line to be entirely within the solution space. Is it okay? So this would be a convex solution space, and therefore one of the corner points of this feasible solution space, which can be called as corner point feasible solutions, which are O, A, B, C and D, are also candidates for the objective, the optimal solution. So that where the objective function is the showing maximum possible value. So you see, for the point O, x1 is 0, x2 is also 0, so z will be 0. Point A, 0 and 100, so z will be 40,000. Point B, 30 and 80, x1 30, x2 80, so z will be 30 into 600, 80 into 400 equal to 50,000. Point C, which is 60 into 600 and 40 into 400, which is 52,000. And finally point D, 80, 0, so 80 into 600, 48,000. So out of all these, the optimal point therefore is very clear that C is our optimal point, which is 60, 40. So therefore the optimal solution is x1 star equal to 60 and x2 star equal to 40 and z star equal to 52,000. Another very important thing, let us also observe that in total, how many corner points are there in this particular problem. Look carefully, O, A, B, C, D, then E, H, F, G, I. As many as 10 different corner points are actually available in this particular problem. Later on we shall see, when we shall try to really find out the basic ideas of the simplex. At that time we shall see that those inequalities, these three inequalities that we have, we can make them as equality by adding one variable each in each of the three constraints. That would actually lead to 5 different unknowns or decision, or 5 different unknown variables and 3 equations. And therefore 5C3, which is about 10, that 10 would be the number of basic solutions, and at this given problem situation, they actually correspond to the corner point solutions. Anyhow, that would be later. So there are as many as 10 different corner points, 5 of them are feasible, and they together create the feasible solution space, and one of them is the optimal solution. So evaluated them, and from there we found that optimal solution, which is at the point C. Right. So this is how these kind of problems are solved also graphically. Let us look at another very interesting problem on linear programming formulation. Example 2. Let us say an assembly requires 2 parts, one each. That is, part A requires 2 minutes in drilling machine and 20 minutes in milling machine. Part B requires 5 minutes in drilling machine and 15 minutes in milling machine. The times include setting as well as loading unloading times. If there are 1 drilling and 5 milling machines and all machines work for full 8 hours, how many part A and part B should be produced each day so as to maximize total number of assemblies? So what is happening in this particular problem? See, the assembly requires two parts, part A and part B. Part A requires work on drilling machine as well as milling machine. Part B also require work on drilling machine and milling machine. So what is it that we want here? We can say that okay, there are two unknowns. X1 is the number of part A, X2 is the number of part B. But question is not that. Question is that how many part A and part B should be produced each day so as to maximize the total number of assemblies. So here basically the problem is how many assemblies are going to be obtained and not really part A and part B. And let us say, so what is the objective function? Objective function is maximize number of assemblies. But how do you know how many assemblies are to be produced? So that is one of the very important question in this particular problem for the purpose of formulation. There is a second point also. The second point is that part A requires 2 minutes in drilling and 20 minutes in milling machine. Is it not? And we have a one full day of working. So that is, and we are also, usually whenever you are working with machines, there are other times required, that is the setting time, loading time, unloading time, jigs and fixtures, then worker fatigue. Then we also have, the people coming and going, shift changes, the shift beginning, some maintenance work. There could be various other kind of situations like, the tea breaks. So all of these different kinds of situations can also be arising, but we are assuming that their effects are not there. That means full 8 hours are actually also available. So obviously we cannot make as many part A and as many part B as we like to be interested. So there would be certain limitations. So here you see we have put those constants here. So suppose we take x1 is the number of part A produced and x2 is the number of part B produced. We have got 2x1 plus 5x2 less than equal to 480, that is from the drilling machine point of view, and 20x1 plus 15x2 less than equal to 2400 from the milling machine point of view. Question is, how did we get that? Let us go back to the problem once again. Say total we have 8 hours. So in minutes terms, how many minutes are available? 8 into 60, that is 480 minutes are total available. Now, how many milling machines and drilling machines are available? Let us say we have only one drilling machine and 5 milling machines. So how many drilling machines hours are available with us? 8 hours. How many milling machine hours are available with us? 8 into 5, that is 40 milling machine hours. So 8 drilling machine hours and 8 into 5, 40 milling machine hours are available with us. Now part A requires 2 minutes in drilling machine, part B requires 5 minutes in drilling machine. Is it not? So what really happens when it comes to the milling machine, the drilling machine, part A is 2 minutes, part B 5 minutes. When it comes to milling machine, part A requires 20 minutes, part B requires 15 minutes. How much drilling machine hours are available? 8. How much milling machine hours are available? 8 into 5, 40. 8 hours is equal to 480 minutes and 40 hours is equal to 2400 minutes. So with all these different considerations, now you can see from the drilling machine point of view, 2x1 plus 5x2 should be less than equal to 480 drilling machine constraint, and 20x1 plus 15x2 should be less than equal to 2400, that is the machine constraint. Now comes what should be our objective function and how do we model maximization of the assemblies. See, an assembly requires one part A and one part B, right? And we need to maximize the total number of assemblies. So how do you, supposing you see at the end of the day, suppose we have 20 part A produced and 30 part B produced, right? So how many assemblies will be produced? Think over. See, there are 20 part A is produced, 30 part B is produced, let us say at the end of the day. So how many assemblies will be produced? Look, get over that problem again. The one assembly requires one part A and one part B, because an assembly requires two parts, one each. Since this is the case, we cannot have 20 part A and 30 part B. We cannot have more than 20 assemblies only. Alright, so if you simply maximize production of part A equal to that is not the answer. What happens if part A's are produced in 30 and part B's are produced in 20? So neither maximizing part A nor maximizing part B is the answer. We cannot really have an objective function maximize part A and maximize part B. Can we maximize part A plus part B? Look here, supposing the production system is such that you are producing more and more of part A. What will happen? Next day the part A would be even more available. So supposing if today you are producing 10 extra part A's, tomorrow those 10 extra part A's will be available as stock, is it not? So producing more of one part is not an optimal decision, because in the next day's production it is going to create a difficulty. So we have to see that the number of assemblies should be neither part A nor part B. So what is it? The idea is that the number of assemblies produced should be less than the number of part A or the part B produced. So in fact it would be equal to x3 equal to minimum of x1 and x2. What is x3? x3 is the number of assemblies produced. So x3 will be minimum of x1 and x2. So if we go back, then our objective function is minimize x3 equal to maximize assemblies, that is x3 equal to minimum of x1 and x2 subject to 2x1 plus 5x2 less than equal to 480 and 20x1 plus 15x2 less than equal to 2400, and obviously x1 and x2 both are greater than equal to 0. There is a problem in this. What is the problem? See, everything is fine, but it is not a linear programming problem. You see, the linear programming requires the objective function should be linear, constraints should be linear. Here both the constraints are linear, no issue itself. But is this a linear function? x3 equal to minimum of x1 and x2? This is not. So you cannot use the minimization function as your objective function. Objective function is maximizing, that's fine, but maximizing z or x3 here equal to minimum of x1 and x2 you cannot write. So what can be done? How do we solve this particular problem? How do we really model such kind of situations where assemblies are involved? So what can we do? So you see, An assembly requires part A and part B, and when you are basically trying to maximize assemblies, idea is to consider a new variable x3 equal to the number of assemblies produced, and you simply say objective function equal maximize z equal to x3. So that's a linear function. There is no issue at all. Is it all right? So now it looks much better. Objective function maximize z equal to x3. But how to model x3? The x3 is the minimum of x1 and x2 that you know. But how do you model it? Because if you write then x3 equal to, suppose you have those two constraints, 2x1 plus 5x2 less than equal to 480 and 20x1 plus 15x2 less than equal to 2400. If you add additional constant that x3 equal to minimum of x1 and x2, that is not going to be a linear constant. See, first we have problem with the objective function. Then we decided we simply say minimum of x3, maximize x3. That's fine, no problem at all because that's a linear function. But you cannot add a constant x3 equal to minimum of x1 and x2. So how do you model these under situation? We cannot keep these minimization function in that form. We cannot keep. So how do you model x3? Think over little bit. Now one thing you see, one part A and one part B together they make one assembly, right? So one assembly requires one part A and one part B. So if x1 is part A, x2 is part B, x3 is assembly, tell me x3 is bigger than x1? No. x3 is bigger than x2? No. So can you say that x3 is always going to be less than both x1 and x2? Is it not? So that is the answer really. Now you can simply model these in this manner, that number of assemblies produced x3 equal to x3 is less than equal to x1 and x3 is less than equal to x2. So that would ensure, because if x1 is bigger, then x3 less than equal to x1 is not a very important constant, but x3 less than x2 will determine that assemblies are less than both part A and part B. Is it all right? Actually, x3 would be equal to the lower of the two. Suppose x1 is 30 and x2 is 20, then x3 should be equal to 20. So what would happen, because you are maximizing x3, x3 would always take the best possible value. And that best possible value in this particular case, when x1 equal to 30 and x2 equal to 20, will be 20. Is it not? Suppose x3 is 19, then you have not maximized. So the problem is, the solution is that in this particular case, it is not really the value or the constant type, because it is a maximization problem. That is where x3 equal to minimum of x1 and x2 is ensured, because you are maximizing x3. So that you must remember. So you can do certain changes in the constant type and so as to linearize by looking at the nature of the problem. That is a very important thing. Alright, so by consideration of the nature of the problem, you can definitely make certain simplifications, and those simplifications can help. But you must also realize that end of the day, what you are really trying to go for, it is also possible to have. Fine, so that is exactly, so this is our final formulation, that x1 is the part A to be produced, x2 is the part B to be produced, and x3 is the assemblies to be produced. Objective function maximize z equal to x3 subject to constraints 2x1 plus 5x2 less than equal to 480, that is the drilling machine constraint, 20x1 plus 15x2 less than equal to 2400, that is the milling machine constraint, and x3 less than equal to x1 assembly constraint, x3 less than equal to x2 another assembly constraint, and x1, x2, x3, they are all greater than equal to 0. So that would be the complete formulation of this particular example. Alright, so you have to understand how step by step, you can take care of all the possible considerations and come up with a very good formulation which is both linear and also fulfilling all the required criteria. Let us take another problem. In this particular problem, it is like this, that in a chemical process, there are two products A and B which are produced. Both products need two operations for the production. A requires 2 units of a certain raw material in operation 1 and 3 units in operation 2 per unit. B requires 3 units of the same raw material in operation 1 and 4 units in operation 2 per unit. And the total raw material available is 16 units in operation 1 and 24 units in operation 2. Apart from this, there is a byproduct C which is also available whenever product B is produced. So 2 times the volume of product B. However, there is a clause. Only 5 units of this byproduct is profitable. If produced beyond 5 units, it has to be destroyed at a cost of rupees 2 per unit. Right? So you see what is happening. Two products are produced, A and B. A requires certain raw material in two different processes in certain quantities. B also requires the same raw material in two operations but in different quantities, and we have total raw material available for operation 1 as well as operation 2. So this will give us some constraints. But there is an additional thing. What is that additional thing? A byproduct is also produced every time we are producing product B, 2 times in volume. But the problem is that only 5 units of this byproduct is profitable, not the entire amount. So what is going to happen? If you produce more than 5 units, you have to then destroy it at a cost of rupees 2 per unit. So not only there is no profit for the additional byproduct, but there is a loss actually of 2 units per byproduct, unit of byproduct. So these are the profit coefficients: 4 for A, 10 rupees for B, and 3 rupees for C. That is the profitable part of the byproduct, per unit. So what you have to do, how much of the products are to be produced in order to maximize profit? So I would ask you first, how many unknowns are you going to take? If you take only 2 units, that is, product A x1 and product B x2, the constraints can definitely be written, but how will you look into byproduct part? And if you do so, then how do you really account for that first 5 units are profitable and beyond 5 units that is not profitable? So this is the issue that is here in this particular problem. So let us say, suppose you take only 3 variables. X1 is the product A produced, X2 is the product B produced, and X3 is the byproduct C produced. So two constraints are very straightforward from the raw material consideration. 2x1 plus 3x2 less than equal to 16 and 3x1 plus 4x2 less than equal to 24. So no issue there. Why? Because the raw material 1 is available, that is 24 units are available, 16 units are available and 24 units are available. So in the first process 16 units, second process 24 units. How many you require? You require A 2 units of in the first process, B 3 units in the first process. So that is 2x1 plus 3x2. In the second process, A requires 3 units and B requires 4 units. So that is what for the first process 2x1 plus 3x2. 2x1 for A, 3x2 for B. 2x1 plus 3x2 should be less than equal to 16 and 3x1 plus 4x2 less than equal to 24. But the question comes then how to model for the x3, that is for the byproduct, right? What about the objective function? Because you cannot simply write 4x1 plus 10x2 plus 3x3 because the entire byproduct is not going to be x3. There will be some units that is to be destroyed, and how much? Only 5 units are profitable. So certain lots of gaps are already there. Now question is, how do you fill up these gaps? So let us now look at it in a slightly different way. That is, instead of 3 unknowns, suppose we take 4 unknowns. x1 product A produced, x2 product B produced, x3 profitable part of byproduct C, and x4 destructive part of byproduct C. Is it not? So now it is very clear that if we make 4 different variables, we can very easily express the whole thing. The x1, so it is a good thing that whenever you have a linear programming situation, it is good to take as many variables as you require. If you do so, expressing the problem becomes easier. Later on, if you want to simplify, you can perhaps reduce certain variables and make the problem simpler. But in the beginning, take as many variables as you might be requiring. So having said that, so if we have these 4 different variables, the objective function is pretty straightforward. Maximize z equal to 4x1 plus 10x2 plus 3x3 minus 2x4. So we have no difficulty there. What would be the constraints? So we have already got 2 different constraints, that is 2x1 plus 3x2 less than equal to 16 and 3x1 plus 4x2 less than equal to 24. So they will remain as it is. But we have some additional constraint, 2x2 equal to x3 plus x4. Where from it comes? Because the byproduct is twice the volume of the product B. So if product B is x2, twice the volume is 2x2. So 2x2 is the total amount of byproduct produced, which is both profitable part and the destructive part. Now x3 is less than equal to 5. That is also very clear because beyond 5 units it has to be destroyed, right? So x3 is less than equal to 5. That is also fine. But now we have additional constraint. What is that? The 2x2 is the total byproduct produced. If the total byproduct produced is greater than equal to 5, then x4 will come into the picture. But that is taken care of, 2x2 equal to x3 plus x4. There is no problem at all. But the difficulty comes is that, and since x3 is less than equal to 5, so here if the 2x2 is more than 5, then it is very clear that x3 would be 5 and remaining portion will be x4. So there is no difficulty because this constant would take care of that. But what about that 2x2 less than equal to 5, that if the total byproduct produced is less than equal to 5, then also there could be some x4 by the nature of the problem, because look here, you have taken a variable x4, it can assume any value. So how do you ensure x4 equal to 0 if 2x2 is less than equal to 5? Is it not? How to make use of these nonlinear constraints? See, it is a nonlinear constraint because an if is included here. So this particular constraint is going to create a difficulty for us. So how do you handle this? Can this constraint be removed, or can this constraint be changed in any other manner? Can it be expressed in another way? Can you think over this? What could be the possible way of modeling this particular thing? Look here, the formulation, what we can make. So before, let me write down once again, this is the complete formulation that is written here. x1 is product A produced, x2 is product B produced, x3 is profitable part of C, x4 is destructive part of C, objective function 4x1 plus 10x2 plus 3x3 minus 2x4, subject to 2x1 plus 3x2 less than equal to 16, 3x1 plus 4x2 less than equal to 24, 2x2 equal to x3 plus x4, x3 is less than equal to 5, x4 equal to 0 if 2x2 less than equal to 5. Question is how to make use of these nonlinear constraint and all the variables are greater than equal to 0. See, the objective function is one of maximization. Let us say a particular solution that x1 equal to 10, x2 equal to 2, x3 equal to 3 and x4 equal to 1. See, forgetting x1, is it not? Forgetting x1, whatever the value, let us say if x2 equal to 2, then 2x2 is 4. Now, if you have x3 equal to 3 and x4 equal to 1, you know what is the total profit? Forgetting the x1 part, 10 into 2, that is 20, 3 into 3, that is 9. So 20 plus 9, 29, minus 2 into 1, 2. So that is 27. Right? So you see what really happens if x2 equal to 2, x3 equal to 4 and x4 equal to x3 equal to 3 and x4 equal to 1, because x2 2, so 2x2 it should be equal to 4. So if x3 equal to 3 and x4 equal to 1, the forgetting the x1 part, the objective function value would have been 10 into 2, 20, 3 into 3, 9, so 29, minus 2 into 1, 2, that is 27. Right? The total objective function value apart from the product A would have been 27. But take this solution x2 equal to 2 and x3 equal to 4 and x4 equal to 0. So if it is 2 and x3 equal to 4, so 10 into 2 is 20, 3 into 4 is 12. So 20 plus 10, 32, 20 plus 12, 32, and this is 0 anyway. So 32 would have been the contribution if we have x4 equal to 0. So look here, at any time if 2x2 is less than equal to 5, you know x4 equal to 0 is always going to return a better solution, because the problem is one of maximization. x4 profit coefficient is negative, so x4 would not come into the basis until unless the full benefit of x3 is realized. Is it not? So therefore, unless x3 is restricted to less than equal to 5, if x2 is just 2, so x4 can be as high as 4. So always that is going to happen. So x4 equal to 0 when 2x2 less than equal to 5 would be ensured by the maximization function. So what we can do? We can simply drop that particular nonlinear constraint. That is what has been written here. We can simply drop the nonlinear constraint while solving in LP, because LP will ensure that x4 will not come into the basis till full quota of 5 of x3 is exhausted, because profit coefficient of x3 is 3 and x4 is minus 2, and it is a maximization problem. So you see, both in the assembly problem and in the byproduct problem, we have exploited the nature of the problem. In the assembly problem, we had a minimization function, but that minimization function we simply removed and we took, the assemblies are less than x1, assemblies are also less than x2, and still managed because the objective function is maximization. So assemblies would be as many as possible, and it would be nothing but the lower value of x1 and x2. In the byproduct problem, similarly, we have also been able to, take care of a nonlinear constraint. We can simply drop that constraint by a suitable consideration of the maximization function, and we could see that the problem could be solved without considering that particular constraint. So the thing to learn here, that while you formulate, the real life is very complex. Not every time you are going to get a clear-cut linear programming formulation. Sometimes you may have to linearize a function. Sometimes you may have to drop a constant. Sometimes you have to see that that constant is not going to come. Maybe the nature of the problem is such that that nonlinear constant will be always redundant. So if we can ensure such kind of situations, then we can still solve the problem with the linear programming approximation, and we can definitely get benefit of the linear programming. What is the benefit of the linear programming? Let's go back to that graphical solution once again. The benefit is very simple. This is our feasible solution space O, A, B, C, D, and in this feasible solution space, the optimal solution is lying at the corner points only. Right? One of the corner points are my optimal solution. Supposing if any of the constant lines would have been nonlinear, or the objective function would have been nonlinear, maybe we would have to see all the points within the feasible solution space as possible candidates. Right? But here we got the greatest advantage, that the optimal solution is nothing but one of the corner points. So that is the greatest advantage of linear programming, that solution lies at one of the corner point feasible solutions. So therefore, if we can linearize the objective function, we can linearize the constraints, and it is possible to do that, it is always worth to go for such kind of situations. Is all right. So that's what we should do in such kind of problems. So having said that, let me now see one more problem quickly. So this is also another formulation problem, that is example 4. Now a house builder is about to develop a plot of land with an area of 10,000 decimals. Two types of houses will be built, standard and luxury. The standard house sells for rupees 10 lakhs. Each standard house requires 10 decimals of land and is occupied by 6 people. Each luxury house requires 20 decimals of land and sells for 15 lakhs, and 4 people occupy each such house. The builder finds it easy to sell the standard houses, and hence he has to restrict construction so as to build at least 2 standard houses for each luxury house. Local Urban Development Authority will not allow more than 320 houses to be built on the 10,000 decimals, and the total number of people living in the new housing complex must not exceed 1600. Determine graphically the optimum number of standard and luxury houses to be built by the builder. The second part of the problem says a special promotional effort can completely remove the restrictions on the number of luxury houses to be sold. What is the maximum money that can be spent on these promotional effort to gain advantage? So there are different parts to the problem, but anyhow the problem is basically a 2-variable problem. How many standard houses to be built and how many luxury houses to be built. So let us say x1 standard houses and x2 luxury houses. Now what should be the objective function? The objective function is, how much money the builder is going to make. So that is also quite simple, that standard house sells for rupees 10 lakhs and the luxury house sells for rupees 15 lakhs. So obviously the maxima is z equal to 10x1 plus 15x2. And what are the different constraints? The constraints is, the first constraint is that of the land constraints. The standard house requires 10 decimals, luxury house requires 20 decimals. How much land is available? 10,000. So that means 10x1 plus 20x2 should be less than equal to 10,000. So that is the constraint with regard to the total land area. Then there should be a constraint of how many people can be occupied. The standard house can occupy 6 people, luxury house can occupy 4 people. So 6x1 plus 4x2 should be less than equal to 1600, because you cannot exceed the total number of people living in such houses. It is also said that you can only make 320 houses maximum. That means x1 plus x2 should be less than equal to 320. So that is another constraint. But also there is a constraint that at least 2 standard houses are to be built for each luxury house. That means if I make 10 luxury houses, I must make at least 20 standard houses. Is it not? So if x1 is the standard houses, 2x1 is 2 times of standard houses. So x2 should be less than equal to 2x1. So that is another constraint. So all of them are put here. I'm sorry, 2x2 should be less than equal to x1. That is because that supposing standard houses are 20, luxury houses are 10. So 2 times of luxury houses is 20. So that should be always looked into. So let us see the constraints. The objective function maximize z equal to 10x1 plus 15x2. That is about the the price, because 10 lakhs is the price of standard house, 15 lakhs is the price of the luxury house. So this is the objective function. What is the land constraint? 10x1 plus 20x2 less than equal to 10,000. People constraint 6x1 plus 4x2 less than equal to 1600. House number x1 plus x2 less than equal to 320. Selling restriction, supposing x1 is the total number of standard houses, that should be more than 2 times the luxury houses. So that means read it very carefully, that there should be at least 2 standard houses for each luxury house. So suppose luxury house is 10, standard house is 20, that means 10 into 2, that is 2x2 should be less than equal to the x1. So this is how we have all the different constraints, and non-negativity constraints x1 and x2 both greater than equal to 0. So having said that, this is our formulation of the problem. Let us also graphically see whether we can solve this problem. So graphically all these lines are plotted. So what has been seen, that look here, this is our x1 axis, this is our x2 axis, this is the line which is x1 plus x2 equal to 320, this is the line 6x1 plus 4x2 equal to 1600, this is the line 10x1 plus 20x2 equal to 10,000. So you see all are less than equal to type, all of them are less than equal to type. So that means all inequalities are all towards the origin, but this line, that x1 equal to 2x2 and originally the constant is x1 should be less than equal to 2x2, that means this line is this way. So x1 should be higher. So therefore the common area is actually OBD. So OBD is our solution space, and in this case point O, that is origin, is 0 0. So in the origin the solution actually is z equal to 0. Point B, which is the this particular point, which is the obtained by the intersection of 6x1 plus 4x2 equal to 1600 and 2x2 equal to x1. So that point is 200 and 100, and their value is 3500. and at point D, which is 2660, that value is 2660. So the optimal solution lies at point B, and that is going to be our optimal solution. So there is a second part. The second part says a special promotional effort can completely remove the restriction on the number of luxury houses to be sold. What is the maximum money that can be spent on this promotional effort? So let's go back to the graph. So if this line is withdrawn, what should be the solution space? Look at it carefully and tell me. See, if that line is gone, can you see the new solution space should be OACD, because this line is gone. So now this portion would be, the entire thing would be our solution space, that is OACD. So that is shown here in this graph. It is shown here that OACD is going to be our new solution space, because that selling restriction is gone. So now we have 4 points: O, that is origin, A, that is 0320, C, that is 160, and D, that is 0260, so 2660. So those are evaluated, and we got at point O it is 0, at point A we got 4800, 320, the luxury houses are to be produced. Objective function is 10x1 plus 15x2. So 320 into 15, 0 into 10, 4800, that is going to be our optimal. The point C is coming out as 4000 and point D is coming out as 2660. So what has happened? After removal of the selling thing, earlier our profit was 3500. After restricting, our profit increases to 4800. So how much profit is increased? The profit increase is 4800 minus 3500. So that means 1300 is the additional profit which we can expect when selling restriction is removed. That means up to 1300 we can actually invest in this particular venture. Fine. So that is all that we have discussed in this particular lecture. And what exactly we have done? We have taken different kinds of formulation problem, and in these different kinds of formulation problem, we have shown some of the solutions also, and some special situations we have modeled also. How to take care of nonlinear situations, how to make them linear by suitable transformations, that also we have seen. And we have also seen that various kind of situations, how the solutions are also to be done by the graphical methods. All right. So thank you very much. And in the next class, we are going to discuss the simplex method. Right. So that is all for today.